Welcome you here to the Kuiper building of the Lunar and Planetary Laboratory. I'm Mark Marley, the director of LPL, and we're really pleased to see all of you at our kickoff for our fall lecture series. Every year we do a fall lecture series on a theme, and as you probably know, in just under 10 days, the sample return capsule from the OSIRIS-REx spacecraft is going to drop off at Earth a sample from the asteroid Bennu. And we're going to hear tonight and during the rest of the lecture series about samples, understanding near-Earth objects, and the possible threat of near-Earth objects. So that's our theme. Tonight we're going to hear from Professor Tom Zega on deciphering the origins of our planetary system through analysis of returned samples. On October 18th, Dr. Veronica Bray is going to talk about the what if, the real-time effects of a Bennu-sized asteroid impact on Tucson. Bennu is the asteroid that the OSIRIS-REx spacecraft visited. And so Dr. Bray does numerical simulations of asteroids impacts and can tell us about what a bad day that would be. And then on November 15th, Assistant Professor Danny Della Justina is going to tell us about exploring hazardous asteroids with the OSIRIS spacecraft. Dr. Della Justina is the deputy PI of the mission. And then after the mothership drops the sample off at Earth, it's going to go on to study the asteroid Apophis in 2030. And that extended mission is being led by Professor Della Justina. And so that'll be another interesting talk to hear. So what we can expect on September 24th, part of the raffle, make sure everybody's one of the raffle tickets, we'll raffle off one of the posters advertising the event. But this happens on Sunday, September 24th. It's at 7 a.m. We're not going to have any kind of public event here because it's so early on a Sunday morning. But you can watch on NASA TV. If you just Google NASA TV, you'll get to the right place. And NASA coverage is going to start at 7 a.m. The capsule will start entering the atmosphere at about 7:40 a.m. We're hoping to see images on TV of the capsule gently descending under the parachutes, and it will land about 7:50 a.m. our time. And then the sample recovery team is going to fly out on helicopters, find exactly where the capsule landed at the Utah test range, and retrieve the sample. Then about 1 p.m. Arizona time, there will be a press conference also on NASA TV. So if you're interested in all of this, definitely turn in to NASA TV bright and early starting Sunday morning, the 24th of September. Let's see, other items of business. For those of you that are here from a class or doing extra credit in class, on the way out after the lecture, you can get a stamp from the folks that are manning the table outside, so, if you need to do that for your professor. And as I said, we're going to raffle off some books and some other asteroid material at the end. So you want to stay tuned for that. So with all that said, let me introduce our speaker, Professor Tom Zega. Tom received his bachelor's degree in geological sciences from Rutgers University in 1996. He received his PhD from a little place up the freeway in Phoenix, Arizona State University in 2003. After that, he did his postdoctoral studies at the Naval Research Lab in 2004 through 2006, before coming back to Arizona to join us at the Lunar Planetary Lab, where he's now a full professor of planetary science. He's also the director of the Kuiper, Arizona Laboratory for Astromaterial Analysis, which is down in our basement. And that's where, as we'll hear, they study materials returned from space, either naturally by meteorites or in the near future, the OSIRIS-REx samples. So with that, I'm looking forward to hear from Dr. Zega all about what we're going to learn from the OSIRIS-REx return. So go ahead, Tom. And real quick, for those of you online, if you have questions, type them into the which box is it, Mary? It's not the chat. It's the there's a question box online. So if you have questions, we'll monitor that and take those questions at the which the Q&A, not the chat. So okay, onwards.
Okay, thank you very much, Mark, for the introduction, and good evening to everybody. Thanks for taking time out of your schedules to be here with us to listen to the first talk in the lecture series for the fall of 2023. The last time I gave one of these talks was about a decade ago now, and the series is really a wonderful outreach event, and it's a pleasure to give one of these lectures this semester. So as Mark noted, sample science is topical right now for reasons that are probably obvious to many of you or will become obvious through the course of the talk. And so I'll discuss what I like to call relics of a time long past and how we can use those to decipher the origins of our planetary system. Okay, so before doing so, it's worthwhile thinking about the picture, a big picture first. This is something we remind our students of frequently. Big picture is very important. And we're all, of course, familiar with the basic architecture of our solar system, i.e. the sun is sort of at the center here. The terrestrial planets are orbiting on the around the sun. And then outside of the terrestrial planets, we have the gas giants, Jovian planets, so on and so forth. And then the asteroid belt sits somewhere between the orbit of Mars and Jupiter, okay? And when we view such a sort of cartoon schematic, the system looks quite structured and familiar, but it wasn't always so. At least we don't think it was always so. Okay, the solar system itself, we think, formed some 4.5 billion years ago within what is referred to as a molecular cloud. Such clouds exist in interstellar space, and they contain mixtures of gas and dust inside of them. And some of these clouds are nurseries for new stars and planet-forming disks. And among the most famous of such clouds is what has been dubbed the pillars of creation, which occur in the Eagle Nebula. And it's about 6,500 light years from Earth. It contains these giant pillars, and giant's really not even a good way to describe them. They're some 9.5 light years high, and if you don't like to think in light years, there's something like 90 trillion kilometers. And if within these pillars are dense clumps of gas and dust, where scientists believe that stars are actually forming. And the center of these clouds can contract. They can form what we refer to as protostars. Temperatures can get high enough to ignite thermonuclear fusion, and it can collapse the cloud and form disks of gas and dust around them that rotate as they shed angular momentum by ejecting material outside of them. And this is sort of a cartoon schematic just depicting that whole process. But this is a pretty accurate depiction of what we know goes on in some of these environments. And by way of example is a series of Hubble Space Telescope images that were acquired over the years 1995 through 2000. So a 5-year set of images taken by HST showing jets from a star called HH30 and actually in the process of forming one of these disks. And over time, the dust and the gas within these disks can actually get sorted out, and material can accrete to form things like pebbles and stones, and ultimately on the pathway to forming planets themselves, okay? And again, this is sort of a cartoon schematic, but the reality is not at all far from that schematic. And here's a really good example of that on the slide here, okay? So this is a radio telescope image on the right here of a planet-forming disk around a star called HL Tauri. It's a young star. It's located about 450 light years from Earth, and this is a newly forming disk around that star itself. And you can probably make out the circular lines in the image at different radial distances away from the center here. And those are where scientists believe that planets are forming, and they're sculpting out the dust and the gas in the disk as they orbit and they grow around the young star. And this remarkable image was acquired by a set of radio telescopes called the Atacama Large Millimeter Array, or ALMA. These are located in the high desert in Chile, and this image was acquired in 2014. And it was a truly remarkable image when this first appeared, because it confirmed a lot of what we suspected was going on in these disks and how planets themselves were actually forming. Okay, but accretion itself to make things like planets is not 100% efficient, and there's material that actually is left over in the form of asteroids and comets, meteors, and in fact, dust, okay? And it's samples of these kinds of objects that we can get, we can obtain samples of, and we can get them in the laboratory and study them with some of the most sophisticated analytical techniques on the planet. Okay, so let's ask the question, what are meteorites? Well, meteorites are rocks from space, and they've often been described as shooting stars. They're not really stars. They're pieces of asteroids, and I think this video, if it works properly. So I've got two videos here that show a meteor coming through the atmosphere on Friday night, October 1992. This one here was in Cleveland, Ohio, and it's recording the fall of the meteorite as it was crossing the eastern seaboard. And it was one of the most historic meteorite falls in record because it fell on a Friday night when lots of people were at football games, right? And so they had their cameras available to them, and they were able to take pictures and film part of the fall. So that one was taken in Cleveland, Ohio, and then here's another one from Johnstown, Pennsylvania. I don't have sound on this one, but it was working its way across the eastern seaboard, ultimately ending up in Peekskill, New York, where it finally landed and adopted its name as the Peekskill meteorite. So it's just about the end of that video, and you can see specks of the meteor as it's progressing through the atmosphere. Okay, so here's what it actually looked like where it ultimately fell in Peekskill, New York, which is just north of New York City, and it hit this lady's red, I think it's a 1980 Chevy Malibu at something like 7:50 p.m. Local Eastern Standard Time. I think I was in university at that time. I don't remember hearing about the fall, but clearly it was documented very well. It had been traveling through space at around 8.8 meters per second, which is about 32,000 miles per hour, but it ultimately slowed to a speed of about 164 miles per hour on impact. And the car's owner, this lady here, she heard the collision from inside her house and described it as a car crash, and she went out to find her car smashed with a 27.3 pound meteorite sitting below it that was still warm, and it had sort of a sulfurous odor to it. She retrieved the meteorite, and then she sold it to a consortium of dealers for about $50,000. So if any of you are looking for alternative careers at this point, think about meteorite. Yeah. Okay. Here's another example that happened a little more recently. So this is the Chelyabinsk fall, and it happened in February 15th of 2013. It was a 59-foot diameter meteor upon entry, weighing about 10,000 tons. It entered Earth's atmosphere at around 19 kilometers per second, or about 43,000 miles per hour. It had a kinetic energy of about 400 to 500 kilotons of TNT before the atmospheric impact and slowed it down. But most of this energy was really absorbed by the atmosphere, creating a shock wave. And I think if this link works, we can watch a video of this. Of course, we have to watch it come first.
Yes to fresh with Mentos gum.
Plus, it comes in a durable paperboard gum bottle that can weather pretty much anything. Anderson
So
Cooper.
this is a CNN clip from around 2010 that documented the
images look like something
fall.
out of a movie. A tiny asteroid tearing through space at a speed of 33,000 miles per hour before streaking across southern Russia. Cameras caught sight of the white trail as it headed across the sky. And then this. An explosion of light, then a massive sonic boom. Strong enough to shatter windows and damage buildings. There were reports of more than 1,000 people injured, mostly from glass and debris. This video shows a children's judo class. Windows blew out here and in buildings around the region. Some people said they thought it might have been a plane crash. This is the aftermath of the blast in a high school. A 17-year-old student put this video on YouTube, showing the reaction in his physics class. Students screamed and ran into the hallways. He said some in the class thought war had started. Some of the incredible images were caught on cameras placed inside Russian cars. Many drivers now record their journeys in case of crashes or run-ins with police. Shock and gasps at the blinding light, the boom, and all the shattered glass.
Asteroid. Реально.
Jim Bolden, CNN, London.
Yeah, so I don't know if you picked it up there, but he actually said, one of the gentlemen said asteroids. So they sort of had an idea of what it might be, although many people were frightened that this actually was, that they were being attacked because of the light and because of some of the sounds. Okay, an example a little closer to home is Meteor Crater, Arizona. So maybe some of you have been there. So Meteor Crater is located in the northern part of the state between Flagstaff and Winslow, Arizona. And the crater itself was formed by the Canyon Diablo meteorite, which impacted about 50,000 years ago. The crater itself is about 3,900 feet in diameter, and it formed from an impactor that we think measured about 160 feet across. Okay, so you don't need a large object to form large craters, depending on what kind of kinetic energy they have as they enter Earth's atmosphere. And this is one of the largest samples of the meteorite that was recovered from this area. And if I'm not mistaken, we have one. Isn't there one sitting out on Flanger, Mark? I think that might be Canyon Diablo, if I'm not mistaken. But this is what it looks like, just to bring it a little bit closer to home. Okay, so where do meteors and meteorites come from? They come from asteroids, and most of which reside in the asteroid belt, right? So this is a not-to-scale model of our solar system with the sun at the center. And as we progress outward, Mercury, Venus, Earth, Mars, and then Jupiter, and the asteroid belt sits between Mars and Jupiter. This is the main asteroid belt, okay? And as of, let me see if I can play this video, as of this week, we checked, there are 1,298,410 known asteroids that are residing out here in the main belt, right? Here's the sun, Mercury, Venus, Earth, Mars. The orbit of Jupiter is out here somewhere. And we have asteroids sitting here in the main belt, more than 1 million of these things, okay? That being said, there are millions of asteroids that are unknown. At least we think there's millions of unknown asteroids. The largest that we know of right now are asteroid Ceres, which is something around 950 kilometers. And then the next one is Vesta. That's something around 520 or so kilometers. And both of these were visited by the Dawn mission some years ago. And if you're interested in the Dawn mission, you can Google that and look that up. Okay, so a little bit about meteorite taxonomy. After centuries of scientists collecting and studying meteorites, we have developed a classification scheme. And meteorites are basically grouped into whether or not they are something called chondrites or non-chondrites. Okay, so you see chondrites over here, non-chondrites over on the other side. And then those of chondrites are actually subdivided based on their bulk chemical composition, and then something called the petrologic subtype, which represents the chemical processing experienced by the meteorite itself, okay? So you can see there's carbonaceous chondrites, and then there's different subtypes of those carbonaceous chondrites. Then there's something called ordinary chondrites, so-called because they're the majority of meteorites that fall on Earth. So something like 80% of all falls make up ordinary chondrites. If we move a little further to the right on this chart, there's something called the enstatite chondrites, so named because of the major mineral phase that they contain, a mineral called enstatite, which is a magnesium silicate, MgSiO3. And then on the other side of this chart here is a set of meteorites called non-chondrites. There are some that are very primitive, others that are so-called differentiated. We don't need to get into the details of what that actually means at the moment, but you'll notice there are some other groups on here that indicate actually that we have Martian meteorites in our collections, which we do. We also have lunar meteorites in addition to lunar samples from the Apollo missions. Okay. But a quick glance at this might actually confuse you when looking at it, and that's because it took scientists many decades of scientific struggle, to put together a classification and taxonomic scheme that really captures all of the different properties of meteorites, okay? And I sometimes liken the analysis of meteorites to leaves on trees. So imagine you were given a leaf of a tree, but you were asked to reconstruct the entire tree from the leaf itself. And in some ways, that's akin to what we almost do when we're studying meteorites. Okay? But in any case, scientists study different groups of meteorites depending on the kind of chemistry they might be interested in, as well as the time scale of that chemistry. Okay, so my group in particular works on a type of meteorites called chondrites. So what are chondrites? This is a nice picture of an example chondrite. So this is an optical image, a picture taken with an optical microscope where we're transmitting light through a very thin sample of it. And this is the meteorite Semarcona. So meteorites get their name by where they fall on Earth. So Semarcona fell in India in 1940. And it's a certain type of meteorite, an ordinary chondrite. The number itself here doesn't matter that much, except for the fact that this is a very primitive and pristine meteorite. It's one of the most scientifically valuable meteorites in our collections. Okay, and it's a chondrite because it's defined by these round objects that you see all over the sample. Those are called chondrules. It's a Greek word, and it means little glassy sphere. Okay. So chondrules measure anywhere from a few hundred micrometers upwards to several millimeters, and they're believed to have been molten liquid, molten silicate liquid at some point, and they crystallized through some process that we don't really know to this day, and it remains an active area of research, the mechanism that form these chondrules. But they're basically the defining characteristic of chondrites themselves. In comparison, this is another type of meteorite. This is a carbonaceous chondrite. Okay, so it too has things like chondrules. So you'll notice this little sphere here, but you'll also notice that it's very dark in color. It has fewer of these chondrules, and the dark material that sort of occurs in between all these little brighter objects is very fine-grained as well. Okay, and that's because it contains lots of carbon and lots of fine-grained materials. So this is a meteorite called the Bell's chondrite. Okay, so different meteorites have different components, and we study different components depending on the scientific question that we're trying to answer. So this is another picture of a meteorite. This too is an optical image. We're transmitting light through it. This is the Allende meteorite, and it has things like chondrules in it. So you see some of these round objects, these spheres of silicates. Okay. It has other things called refractory inclusions, so named because the minerals that make them up have very high melting points, so they're referred to as refractory inclusions. It has grains of metal in it dispersed throughout some of this darker fine-grained material, as well as compounds that contain sulfur. And then all of this other dark stuff that sort of occurs throughout the meteorite is referred to as matrix, and it's sort of a background sea of material in which all of these other coarse-grained objects actually occur. Okay, and Allende, it turns out, is also a very scientifically valuable sample. It's sort of an interesting story about Allende. So Allende fell in 1969 literally months before the first crewed mission to the moon. Okay, so scientists around the country were gearing up for measurements of moon rocks. So all kinds of instruments, electron microscopes, mass spectrometers, etc. And they were ready to measure moon rocks when they came back later that year. And something like over 2 tons of the Allende chondrite fell in a little village in the Mexican state of Chihuahua. El Pueblito de Allende is where this meteorite fell, and it too has become one of our most scientifically valuable samples, in part because it contains lots of these objects here called refractory inclusions, which are among the oldest objects in the solar system. And so by way of example, this is from a not too long ago paper that was published in one of the scientific journals that proved, in fact, that these refractory inclusions are quite old. So you see every one of these red dots here is one of these refractory inclusions. And the data along the horizontal line here show their absolute ages. So we can age date these objects using something called radiochronology. We can measure isotopes that are radioactive. They decay because they're unstable. We know their half-lives, and so we measure the amount of daughter element left over as an isotope decays. We can back calculate how old an object actually is. Okay, so some of these refractory inclusions, sometimes referred to as CAIs, so named because of the minerals that they contain, are very, very old, on the order of 4.568 billion years or so old. Okay, so those objects basically are the time zero stamp for our solar system. Those are what age date our solar system at 4.5, 6, 7, or 8 billion years. Okay, as compared to things like chondrules, those little round spheres that I showed you just a moment ago, those are around 1 to 3 million years younger than these refractory inclusions. Okay, some of them overlap a little bit, but most of them, as we measure them, have age dates that are actually younger. Okay, and so when we get an age on these objects, we can start getting insight into maybe the processes that form them and the spatial kinds of events that were happening in our early solar system some 4.5 billion years ago. And we ask questions about how some of these things form. Did they form through gas-solid chemistry? Did they form through liquid-solid chemistry? Where in the solar system did they actually form? So if we sort of think of the solar system with the sun at the center, this cloud of gas and dust around it, very, very early in its stages, we have some sense of where objects might have formed very close in, like those refractory inclusions, because temperatures were very, very high, close to the sun, whereas some other objects may have formed very, very far out in our early solar nebula. Okay, and we know that there was transport also in the early solar system by way of sample analysis, and I think that's a good segue into talking about sample return missions. So one of the sample return missions that I was involved with some years ago was called the NASA Stardust mission. So the Stardust mission was selected as the 4th discovery mission. Discovery missions are, or were defined as low-cost solar system exploration missions with highly focused science goals. Okay. In the Stardust mission, the objective of the Stardust mission was to fly through the dust cloud surrounding the nucleus of a comet and return cometary material to Earth. Okay. It was launched in February of 1999. It collected cometary dust from Comet 81P, or VILT-2 as it's sometimes referred to, on January 2nd, 2004, and it returned to Earth on January 15th, 2006. And here are pictures of the recovery of the sample return capsule, the SRC, when it landed in the Utah test and training range, which is the exact same place that the OSIRIS-REx sample will land in. So you can see the capsule there. It's landed gently onto the salt flats there. It's being recovered by the recovery team. They safely secure it it gets put onto a helicopter, and then it's brought back to a curation facility at the UTTR before it's flown to Johnson Space Center in Houston, where the sample was actually curated. And here's a picture of the collector tray. So the collector tray is this thing here. You see there's these different cell blocks. Inside of these cell blocks is a material called silica aerogel. It's a very low density material that trapped particles as they streamed off the tail of the comet and tried to pass through the collector tray. You can see scientists are all in bunny suits in this clean room. And then this is the principal investigator, Don Brownlee, signaling the victory salute that they actually collected particles that they could see trapped in the aerogel. And one of the key results of the Stardust mission, I think, is really well captured in the abstract from the first paper that appeared from the sample analysis, which says that the Stardust spacecraft collected thousands of particles from Comet 81P, returned them to Earth for laboratory study. The preliminary examination of these samples shows that the non-volatile portion of the comet is an unequilibrated assortment of materials that have both pre-solar and solar system origins, so objects that formed even before our solar system and were preserved inside of the comet. The comet contains an abundance of silicate grains that are much larger than predictions of interstellar grain models, and many of these are high-temperature minerals that appear to have formed in the inner regions of the solar nebula. Their presence in a comet proves that the formation of the solar system included mixing on the grandest of scales, okay? So there you have it, ground truth information on the makeup of a comet and what it told us about our origins, okay? So what about meteorites? So that brings us to the historic OSIRIS-REx mission. So what does OSIRIS-REx stand for? OSIRIS-REx is an acronym. It stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. Okay, so we will return a sample of pristine carbonaceous asteroid regolith that will be measured here in just a few weeks. As Mark mentioned, the return is on September 24th. We did spectroscopy around the asteroid, providing ground truth for telescopic data of the asteroid population, both in near-Earth asteroids, which we'll talk about in just a moment, as well as the main belt. We mapped the chemistry and mineralogy of the surface. Maybe that helps in identifying potential resources that could be used in the future for all kinds of things. We measured something called the Yarkovsky effect, which we would be concerned about if this asteroid is potentially hazardous, which is believed to be the case sometime in the future. So that's being worked on. And then Regolith Explorer, to document the regolith. Regolith is a word that means rock blanket. So the surface, the very fine grained material on the surface of the asteroid, to document that at the sampling site at scales down to the sub-centimeter. And I'll show you what some of that looks like in just a bit. Okay, so this was the launch on September 8, 2016. I took this picture myself. This was standing at the Banana Creek site near Cocoa Beach, Florida, outside of Kennedy Space Center, where the spacecraft was launched from. If you look in the distance, you can sort of make out the launch tower there. And then obviously you can see the trail of smoke and the rocket making its way into space. I think there is a video that sort of describes the overview of the mission.
OSIRIS-REx is NASA's first asteroid sample return mission. It launched in September 2016 on a journey to explore a near-Earth asteroid called Bennu. After arriving in 2018, OSIRIS-REx spent nearly 2 years orbiting Bennu, mapping and studying its rugged terrain before carrying out its primary science objective. On October 20th, 2020, the spacecraft ventured to a small crater in the asteroid's northern hemisphere. It dodged jagged rocks and towering boulders and plunged its arm into the loose surface, excavating 6 tons of debris while collecting about 250 grams of material. OSIRIS-REx stowed its bounty and closed its sample return capsule. It bid farewell to Bennu in May 2021, embarking on a 1.2 billion-mile cruise back to Earth. Now, 2 years and 4 months after leaving Bennu, OSIRIS-REx is closing in on the place where its journey began. On September 24th, the spacecraft will approach to nearly 63,000 miles from Earth. It will power up and release its sample return capsule at 4:42 a.m. Mountain Time. The capsule must be jettisoned within a narrow time frame and at just the right angle to hit its target, an area of roughly 250 square miles in Utah's West Desert. Once the capsule is away, OSIRIS-REx will fire its thrusters to avoid colliding with Earth. At 8:42 a.m., the capsule will streak into the atmosphere at a blistering 27,000 miles per hour. It will race across the western U.S. and begin to glow with heat, allowing infrared trackers on the ground to chart its progress. As it pushes deeper into the atmosphere, the capsule will rapidly decelerate, subjecting the Bennu samples to a punishing 32 Gs. About 2 minutes after entry, it will slow to Mach 1.4 and deploy its drogue parachute, stabilizing its descent. The capsule will enter special use airspace at 8:46 a.m., almost 10 miles above the Department of Defense Utah Test and Training Range. Radar stations will lock on and track it to within 30 feet of its landing site. At 8:50 a.m., the capsule will extract and deploy its main parachute 1 mile above the ground. It will make its final descent at a leisurely 11 miles per hour, like a marathon runner savoring a victory lap, before touching down in the desert soil at 8:55. After ground teams retrieve the capsule, the Bennu samples will be taken to NASA's Johnson Space Center in Houston, Texas. The sample canister will be opened in the Astromaterials Acquisition and Curation Facility, and the samples will be curated, distributed, and studied for decades to come. Having delivered its cargo, the OSIRIS-REx spacecraft will depart Earth, but its journey will not quite be finished. In a daring encore, the renamed OSIRIS-APEX will enter an elliptical orbit of the Sun, repeatedly passing within the orbit of Venus and pushing the limits of its thermal design. Beginning in 2029, it will chase down and investigate Apophis, a 1,200-foot stony asteroid destined to make an exceptionally close flyby of Earth. After 13 years in deep space, at the start of a new decade, alone on a new world, the journey will continue.
So that's an overview of the mission. Let's give you a little more details about how asteroid Bennu was chosen. So it was chosen in 2005 as the mission target. And in 2005, there were greater than 500,000 known asteroids. As I said, as of this week, there's well over 1 million of these. At the time, there were 7,000 near-Earth asteroids. We'll describe those in just a moment. 192 of these had optimal orbits for sample return. 26 had a suitable diameter that we could touch and go on. 5 of them were carbon rich, and of those 5, Bennu was down selected as the target for the mission. Okay, so I mentioned something about near-Earth asteroids. So if we look sort of at a top-down view of our solar system, again with the sun at the center, Mercury, Venus, Earth, Mars. Here's the main belt that we talked about just a moment ago. And if you look closely, there are red dots that are circling around here in the inner part of the solar system, okay? Those are referred to as NEOs, near-Earth objects. And as of this week, there were 32,671 of those known. Greater than 90% of NEOs are actually near-Earth asteroids. The rest are comets. So the population of asteroids that Bennu was chosen from were part of the NEOs. Okay. So here's a closer up picture of asteroid Bennu. So it's carbonaceous. It's what's referred to as a rubble pile asteroid with a spinning top shape. As I mentioned, it's a near-Earth object. It's got a terrain that's dominated by boulders, which is very rough, and had to be accounted for when we were planning the touch and go maneuver. And OSIRIS-REx spent about 2 years surveying the asteroid and ultimately chose a site that was nicknamed Nightingale. And a sample of the regolith which again is this unconsolidated blanket of rocks and dust, was acquired on October 20th, 2020. To give you a sense of how big Bennu is, there's some familiar landmarks here. So asteroid Bennu is about 510 meters in size relative to the Empire State Building, which is around 443 meters. This is in New York City, obviously. And then the Eiffel Tower here in Paris at 324 meters. So it just gives you a feel for the level of scale for asteroid Bennu. Sample return is the primary objective of the mission. So the key requirements are to return a sample that's greater than or equal to 60 grams of bulk pristine material using a touch and go sample acquisition mechanism, or TAG-SAM is the acronym. And it has a contact area of something like 26 square centimeters. This is just a picture showing the simulation of a mock TAG-SAM device contacting a fine grain simulant that was used as part of the testing. Okay, but it's supposed to contact that amount of area from Bennu using the TAG-SAM and return greater than or equal to 16 grams of pristine material. But we know some things about Bennu already because we spent a couple of years orbiting around the asteroid, taking very high resolution pictures and also doing high resolution spectroscopy. So this is a plot of the infrared spectroscopy that was performed in part on asteroid Bennu. So that's the blue spectrum here. See, here's our legend for Bennu. And then it's compared to infrared spectra that were acquired from well-characterized meteorites that we have in our sample collections here on Earth. So one is the Murchison meteorite. This fell in Australia. ALH is a meteorite that was found in Antarctica. So ALH stands for Allen Hills. So the National Science Foundation and NASA have a program called ANSMET that for decades has gone to Antarctica to collect meteorites. And many thousands of these things have now been returned to us, and they're very valuable samples for our scientific collections. And then another meteorite called Arguet, this fell in France. And so these samples have all been really well studied in the laboratory using a variety of techniques, and we have a really good sense of what they contain. And so they made for good reference spectra when comparing measurements to asteroid Bennu, okay? And without getting too far into the details here, we know that by comparing this blue spectrum here to those that were acquired from these three different samples, that this kind of feature represents water. Water is actually contained in some of the minerals, not just in these meteorites, but we think also in some of the minerals that occur on the surface of asteroid Bennu. So that's very important, right? Particularly since part of the mission is to understand prebiotic molecules on Earth. What else does it contain? So again, we can compare spectra that were acquired from asteroid Bennu to those that were acquired in the laboratory. We think that there are minerals like magnetite. Magnetite is an iron oxide. It has a chemical formula Fe3O4. So we think there are abundant grains of magnetite, possibly some other materials that contain oxygen in them, bonded with metals as well. And also organic compounds. So looking at spectra over different wavelengths and looking at these features in the spectra, comparing them to asteroid Bennu, we can get a sense that Bennu also contains organic compounds, which is really key to some of our science questions that we want to address. Another thing that was learned during the orbital phase of the mission by imaging the surface at high resolution and seeing things like this feature here, which has very, very high reflectivity, we got a sense that there might be veins of material that are scattered throughout the asteroid itself. And then when we did spectroscopy on them, we found that some of these could possibly be minerals that contain carbonate. So calcite is a calcium carbonate, siderite is a iron carbonate, and you can see that these spectra here from Bennu and black are all compared to these standard materials like calcite, siderite, some other carbonates here. But they're all minerals that contain carbonate. Why is that important? Because carbonates form on Earth by precipitating from water, okay? When water solutions become sufficiently saturated in things like carbonate, the carbonate ion can bond with metals and precipitate out as minerals like calcite, so on and so forth. So finding minerals like that in the return sample will give us insight to the kinds of processes that could have occurred on the asteroid at some point in its history, and specifically those that could form by reaction with liquid water, which is a really key part of the science investigation. We were also able to map the surface of the asteroid. So what you're looking at here are a series of pictures that actually map the asteroid over different wavelengths. And so by doing that, we were able to tell the distribution of things like hydrated minerals. So phyllosilicates are minerals, they're silicates, they contain water in their structures. So we could see that there was hydrated phyllosilicates distributed throughout the surface of the asteroid, as well as abundant carbon-bearing material. That could be things like the carbonates I just talked about a moment ago. It could also be organic compounds distributed on the surface of the asteroid. Time will tell when we get the sample back and we're able to look at it. Another thing that was found during the orbital phase. So when we looked at the surface closely, it seemed that there were data suggesting things like these features here that are linked to exogenic boulders. So exogenic means that they could be foreign material, and they seem to have the same composition of some minerals that are part of a group of meteorites called the HEDs, or howardite, eucrite, diogenite meteorites that are believed to come from asteroid Vesta. So there's some suggestion in the orbital data of Bennu that we might actually capture some material that's foreign, that came from another asteroid, possibly even this asteroid here, Vesta, that I talked about a bit ago when we were talking about the main belt, the asteroid main belt. And perhaps the biggest surprise was that Bennu is actually an active asteroid, okay? So this set of images were acquired in January of 2019. And if you look very closely, you'll see that there's some bright dots here on the screen. Over here, there's some others over here. These were particles that were being ejected off the surface of the asteroid, suggesting that, in fact, Bennu has some sort of active geologic process going on, ejecting these particles off of its surface. So this was a very exciting discovery. Okay, how far did OSIRIS-REx plunge into asteroid Bennu? So this is an interesting question, but I think a video probably best describes what happened. So you see the spacecraft, it's descending here. Axam is extended, it's about to touch the surface. Plunges in. Injects nitrogen gas, causing this explosion of particles, fighting the material into the collector. About 9 seconds after contact, thruster is fired to halt the descent, pushes away material from Axam, blasting it all over. It turned out that the arm of the spacecraft had sunk about half a meter below the surface, suggesting that the surface itself was very weak, it was loosely consolidated, and maybe very highly porous. There was estimates that something like 6 tons of material had been excavated from this event itself, and about 30 seconds after contact, it shut off the thrusters and it drifted away from the asteroid. And there's some thinking that if they kept firing the thrusters, the spacecraft itself may have gone through the entire asteroid. It may be that loosely compacted. Okay, after contact, we confirmed that sample was collected. So this was a very sort of nerve-wracking time. So you can see the base of the tag SAM here. These little spherical or circular objects are contact pads. I think Dolores Hill had a table outside before we started the lecture, and she had a sample of one of these contact pads. Those contacted the surface first. They're made out of stainless steel, and they sort of have a mesh to them. So we call it the stainless steel Velcro mesh, if you will. And the idea with the contact pads is as soon as the tag SAM made contact, any fine-grained particles on the very surface could get trapped inside of these contact pads. So why is that important? Well, it turns out that asteroids, they don't have atmospheres. They're referred to as airless bodies. The moon is another example. They experience something called space weathering. So space weathering is the bombardment of the bodies, the surfaces of these airless bodies by the solar wind, by micrometeorites and objects of that sort. And that modifies the surface structure and composition, which affects our ability to actually study these things and investigate them with telescopes and do things like spectroscopy. So we have to sort of decipher space weathering to uncloak what's underneath the surface. And the idea behind the contact pads is that they would collect some of that surface material for the science team to investigate things like space weathering. But you'll notice there's a bunch of particles that are scattered throughout this image. And it turned out that after we collected and the arm of the tag SAM was brought back up to the spacecraft to take a picture of it, the idea was to take a picture and confirm that there was sample in it. We realized that we were losing mass actually quite quickly. The decision was made by Dante, the principal investigator, to stow the tag SAM as quickly as possible so we didn't lose any more of this material as it was sort of being fluidized and leaving the tag SAM. And just doing some particle counting, making some assumptions about things like mass, we came up with a particle count or mass loss estimate of something like 10 grams. Here's what the Nightingale site looked like in March 2019. This was prior to touchdown. Here's what it looked like afterwards. So if I go back and forth a couple times, you'll see that in fact, we created a little crater there, we excavated material, and new material showed up underneath that may in fact even be darker than the surface. So we're hoping some of that material is actually in the tag SAM that will return in just over a week's time here on Earth. The sample was stowed quickly. We estimated based on changes of angular momentum to the spacecraft that the sample mass had something like 250 grams, plus or minus an error of about 100 grams. So we think we exceeded the level 1 requirements to return greater than or equal to 60 grams of material. It has a size range, we think, from somewhere around 3 centimeters to submicron, with a number of different types of materials that we talked about just a moment ago: hydrated silicates, organics, carbonates, magnetite, oxides. Sulfides, we think, are almost certainly in there. These are compounds that are bonded with sulfur. We can't see them because they're not active spectrally, but we infer them from study of analogous meteorites. And then part of our science investigation will be to figure out what the different types of minerals are and what the different rock types might be, or lithologies might be in the return set. Okay, so the SRC will return in just about 2 weeks' time, or just under 2 weeks from now. The science team itself is international in scope. So here's us at the U of A. And there's some other core analytical facilities on the team. One is at NASA Johnson Space Center, another one at NASA Goddard Space Flight Center, and the rest of the science team is scattered throughout the United States, Japan, Australia, Europe, and even in India. But the headquarters for the PI office is here at the Lunar and Planetary Laboratory. And as Mark mentioned when he introduced me earlier, 2 floors below us, we will measure these samples using our analytical facility called K-Alpha, or Kuiper Arizona Laboratory for Astromaterials Analysis. And below us, by two floors below us, we have a world-class analytical facility that can handle samples in multiple geometries and multiple scales. We can look at samples from that sort of hand scale, stones, small particles. We can mount them in different types of media. We can embed them in epoxies. We can polish them flat and probe them with electron microscopes. We can make really, really fine sections using mechanical slicing and ion milling that we don't have time to get into today. But we have a suite of instruments everywhere, anything from the optical microscope that we're all familiar with to electron microscopes down to ion mass spectrometers that allow us to interrogate the sample's isotopic makeup, transmission electron microscopes that allow us to look at the sample down to the atomic level. And the goal will be to determine the chemical composition of the sample, its mineralogy, what kinds of textures it contains, what its organic chemistry looks like, whether or not it has specific isotopes, how those isotopes are distributed in the sample, and how all that information combined can tell us about the history of the sample and the origins of asteroid Bennu. So we will perform coordinated analyses. So all these different instruments exist in our facility. We're able to coordinate the kinds of measurements that we do on the sample using any one of these instruments. And the goal really is to extract the maximum amount of information from the tiniest of particles, right? We want as much information as we can get from the smallest particles because these are ultra precious samples and there's a limit to how much the science team actually gets. So we will do these measurements, we will perform them in a coordinated fashion, we will extract this information from the centimeter down to the atomic scale, and I didn't want people to leave tonight having never seen an atom in your life. So this is an atomic resolution image, okay? So every one of these white dots you see on the screen is actually a column of atoms in projection. So in and out of the screen here is a column of atoms in projection. And this is from a mineral called perovskite. This is its chemical formula, CaTi with 3 oxygen atoms contained in it. And in this kind of image, what you're looking at are the what we refer to as the cations here. So calcium and titanium. We cannot see oxygen in this kind of image, but we can see calcium and titanium. And I don't know if your eye can make it out, but every other row is brighter than the succeeding row. So bright, dark, bright, dark, bright, dark. And that's because using this kind of imaging, heavy atoms like titanium appear brighter than lighter atoms like calcium, okay? So these are the calcium atoms, the titanium atoms, calcium, titanium, and they're all separated by about 300 picometers. Well, what's a picometer? It's 10 to the minus 12 meters. So take a 1, put 11 zeros in front of it, and you've got a picometer. And this sort of gives you a feel for the level of atomic length scale. What's remarkable about this image is primarily 2 things. One, the amount of order that you see in the image, right? Everything is arranged very periodically. You don't see any deviation from any one of these individual positions in the image. And when we look at samples like this, it's often not the perfection of nature that we're looking for. We're looking at the deviation from perfection because that often tells a very interesting story. Not that perfection doesn't tell us something interesting, but oftentimes we're looking for the deviation from that. The other thing interesting about this is that it comes from a sample of one of those refractory inclusions that I discussed much earlier. And those are among the oldest objects in the solar system. When we age date them using radiochronology, looking at the decay of radioactive isotopes like uranium to lead, we get age dates, like I said, of about 4.567 billion years. So what you're looking at here are atoms that literally assembled together 4.5 billion years ago, okay? And we can do that 2 floors below us in the Kuiper facility here at the University of Arizona. And we will do measurements like this on the return sample when it comes back. And we will do them to test what are referred to as the driving hypotheses. I won't read these all specifically, there's too much here, but we will look at the relationship of the sample to known meteorites. We will look at organic history, pre-solar history, the formation age and nebular history. We will look at whether or not the parent asteroid itself experienced alteration, whether or not it was resurfaced. We will look at things like something called the Yarkovsky effect, or what's referred to as the energy balance. We will look at effects of space weathering, and then we will look at whether or not proximity operations, i.e. being around the asteroid itself, whether the tag process or return affected the sample in any particular way. And there's really no telling what we will find in the return sample, but we expect to generate new knowledge. We expect to train the next generation of sample scientists, some who are in the room this evening, and possibly even rewrite textbooks. So what started out in 1969 with the first samples ever returned from a mission, that being the Apollo 11 mission, returning the first extraterrestrial samples from the moon, continued through with the Genesis mission, returning samples from the sun, the Stardust mission, which I talked about a bit ago, the Hayabusa missions that return samples of asteroid Itokawa and asteroid Ryugu, continues today with OSIRIS-REx. And these samples will be a precious resource, providing generations of scientists in the future material to work on. So stay tuned. Okay, so with that, I'd just like to say thanks to a few different groups, to NASA, to NSF, to the U of A for supporting instrumentation in our facility, to NASA for years of supporting our research and enabling transformative missions like OSIRIS-REx, to LPL, the College of Science, the Office of the Vice President for Research here at the University of Arizona for supporting our facility over the years, including many staff members whom I don't have time to really thank properly here, to Mark for inviting me to give the first talk in the series this fall, in the public lecture series, and to many colleagues and mentors around the country and the world. And I think with that, I thank everybody here very much for spending time with me this evening. So thank you.
Sadi, we're all very excited to see what we're going to find out in just starting in just over 10 days or so. Time for a few questions. Any questions from inside the room? How do I get to the online questions here?
Mark, I have the online questions.
Oh, okay, go ahead, Amy. Why don't you?
The question is, if Bennu continues to eject material over a lifetime measured in billions of years, should we assume it was once very much larger?
That's a great question, actually. Should we assume it was much larger? Possibly. One of the goals of the mission is to figure out what the parent asteroid of Bennu was itself. So Bennu itself may have been part of another asteroid at some point in its history. Whether or not it is will be part of our investigation. And it could be that the particle events that we're actually seeing right now are a result of its recent orbits around the solar system, right? Comets do this kind of thing all the time. When they get very close to the sun, they get heated up. Things like ice will sublimate, will eject material off it, and we get the familiar tale of the comet. And so it could be something related to how its more recent history, Bennu's more recent history, as we see it today. But whether or not it was larger, it's an interesting question, possibly. But I think we'll know when we start measuring the sample and get a better sense of what Bennu's parent body might have, or whether or not it came from a different parent body altogether. In which case, maybe that assumption is not particularly valid. But time will tell. TBD.
All right. Are there more online, Amy?
No more online.
Okay. Anything else in the room?
Just a because it's shedding particles.
Wait, one more online just came in.
We have an oral, or we have one here. We'll take the in the room one first. So go ahead.
I'm just wondering if it's going to impact you're going to look at kind of the space weather based on the particles on the surface. But if they're shedding, is that going to affect, it's going to look like there's not as much weather or something?
Yeah, I mean, that's a good question, right? So we don't know exactly what we're going to get, right? And so the point of using the contact pads was hopefully to get some material that was directly on the surface. We don't think all of that material is fresh. Some of it we think probably is weathered. Hopefully some of it's weathered because we want to understand space weathering better by looking at return sample. But again, it will all depend. So we don't think a lot of it has been lost to these ejection events. We think that there should be some stuff on the surface that was weathered, but time will tell.
Okay, then the last one online.
There are actually two now. So the first one is, when you provide dating of celestial bodies, what is the baseline for determining age?
Okay, can you read that again, Amy?
Yes, when you provide dating of celestial bodies, what is the baseline for determining age?
The baseline for determining age. I'm not entirely sure I understand the question, but I'll give it my best answer. So when we determine age, in the way at least I was describing earlier, we determine absolute age. Okay, so we take the sample, we measure it for its isotopic composition, and when we're doing things like trying to age date objects like refractory inclusions, then we're looking at specific isotopic systems. So we'll look at something like uranium and lead. So uranium will decay to lead over time because uranium is a big atom. It has lots of neutrons in its nucleus. Some isotopes of uranium are not stable. They're unstable nuclei and they want to decay. And we know the timescales over which that decay happens, right? That's referred to as its half-life. So we have values for all those things. And by measuring the sample itself, we look for what's called the daughter isotope. So what ends up decaying from the parent isotope. And so by measuring the amount that's left over, by knowing the half-life, we can back calculate how old an object is. There are some caveats to that. For example, if the sample's been heated up in some fashion, if it's been altered in some way, but we have to study it with other types of techniques to understand whether or not those effects have imparted themselves to the sample itself. If they haven't, we can safely say that the date we've determined is the age of that particular material, okay? And so in that sense, it's an absolute measurement. We don't need a baseline to do that. There's other types of chronology that we do, which are relative chronometers, okay? So we don't get an absolute age, we get an age relative to an absolute age. And in that case, then we do in fact need a baseline, and the baseline would be that absolute age. I hope that answered the question.
Okay, and with that, I think let's thank our speaker again. Thanks. Thank you.